Yeah, so hello student. This is third lecture, online lecture series of the course Algebra MA415. Recall in last class we discussed about homomorphisms. Okay, um, homomorphisms. Okay, so you have two groups G1 and G2. They may be different operation also, and you have maps such that it satisfies this property if of say G1 G2 equal to phi G1 into phi G2. Okay, and this is for all G1 and G2 belongs to capital G1. Okay, and so this is structure preserving maps, and this homomorphism has lots of properties. Maybe let me say some of the properties. Okay, so given a homomorphism, we can define something called fiber. Okay, so what is the meaning of fiber? So let me define it. So let you have something say y belongs to G2. This is given to you phi from G1 to G2. Okay, homomorphism. This is given to you, and you choose an element, say G2. So we say that the fiber of y under phi is defined as defined by this set. This is all the f in phi inverse of y. Okay, so this is a set all the pre-images of y. Okay, okay, so yeah, so let me write down by this notation, so it will be easier. Y inverse of y, this is what? This is collection of all those x belongs to G1 such that phi of x equal to y. Okay, it's called the fiber of this, and there is a very nice particularly when y equal to say when y equal to identity of G2, then this fiber has a name, then this fiber is called the kernel of phi. Okay, so what is the kernel of phi? So by definition, kernel of phi we will write down by this symbol car phi. This is defined by collection of all those x belongs to G1 such that phi of x is identity. Okay, identity means identity in G2. Okay, because these images are into G2. Okay, so this is a very specific. So obviously by definition you can easily find out this is a subset of G1, and we will check whether it has some property or not. So property number one of homomorphism, so we can easily check it that image of the identity of G1 is exactly identity in G2. Okay, and this is obvious. So how to prove it? So just let me give you a small sketch of proof. So So you write down this identity of G1 is this product of, so, choose any element G1 G inverse, okay, because you know that if you take any elements, so the inverse product will be identity, right? And now you use the property of homomorphisms, and so okay, so I don't need this thing. I mean, it is even easier to find out. So I can write down 1 into 1 just. uh, Yeah, so this property I don't need here. So this is I can write down just 1 G1, and that is done. And then 5 G1, 5 G1, right? But 5 G1s are elements of G2. This is element of G2. This is also element of G2. And then you talk about cancellation, and this will gives you that. So phi of 1 identity of G1 equal to identity of G2. These are simple properties, and you can say further. For example, you can say that for any G belongs to G1, this phi of G1 G inverse is nothing but phi of G whole inverse. And these properties are also simple. You just use the homomorphism property. So I think you can do this as a homework problem. Okay. uh, just homomorphism property will gives you the proof. Similarly, you can have for any power of any element, so choose any power, and this will be nothing but phi of G. This is also true for all G belongs to G1. Okay, this property are true. Now now for cardinal, you can ask about what about is it a special subset of K, and then you just prove that cardinal of phi is nothing but is a subgroup subgroup of G1. Okay, now how to prove this statement? So um, obviously first of all, this kernel of phi is non-empty, okay, as this identity of G1 is inside kernel, right? Identity always map to identity, so it's non-empty set. And then to prove something subgroup, you recall that in last class we showed that if we have two elements, so let I choose two elements, say A and B belongs to kernel of phi, okay, and then you need to prove that A B inverse also inside the kernel, right? So now to prove if something is inside the kernel, what you need to prove? You need to check that phi of A B inverse is an element, is identity or not. Now how do you check phi of A inverse? So this is again property of homomorphism. It will give you phi A into phi B inverse, right? But we know that phi B inverse equal to phi B whole inverse, right? But phi A is identity because A belongs to kernel, so this is identity. This is also identity. Identity means identity of Z2, obviously. So this is identity of Z2, okay? And hence this implies that A B inverse again an element of kernel, and this proves that kernel is a subgroup, okay, of G1. Okay, similarly you can define another set called image of phi. Okay, so what is image of phi? So image of phi is all those phi belongs to G2 such that um, phi of x equal to y for some x belongs to G1. Okay, so you collect all the points which will be coming as the image of some points of G1. Okay, so this is called the image, and again this is homework. You just show that uh, image is a subgroup of G2. Okay, it's a simple observation. You can easily prove these things. Okay, yeah. So now one more idea we need to check before going to further. So um, yeah, so you remember that inside the group G, we can define something called order of an element. Okay, okay. So see for a okay, so for a group, so we define by this symbol, and this is nothing but the cardinality of group G. So this is nothing but number of elements in G. Okay, but how to define something called order of an element? So let me define it. So define, let say G belongs to G. G be a group that is given. Okay, um, the order of the small g is the least positive integer in, okay, such that what happens, such that g to the power n equal to identity. So what does that mean? Least means what? There does not exist any positive integer less than n for which g power that integer equal to identity. Okay, and if there does not exist such integer, if there does not exist such integer, then we say the g is of order infinite. G has infinite order. Then we say g has infinite order. Okay, and remember this positive is very important. Okay, because you know that for any element, if you take the zeroth power, then it will be identity, right? But zero is not the positive integer, so this positive thing is important. Okay, so G has infinite order. Okay, and with this, and this order also has lots of properties. For example, um, so under homomorphism, you can always ask whether order of an element, what is the relationship between order of an element. So the question, so this question we can come naturally. So you have homomorphisms from G1 to G2, and you can ask what about, so what is the relation between, say you choose an element and you want to know that what is the relation between order of G and order of the image phi of G. Okay, So this question, you can easily answer this question. So let me just briefly discuss something, um, and then you can answer this kind of question. Okay, yeah. So before that, let us discuss some of the properties again, law or order. So, and then you can easily discuss these kind of questions if you answer. Okay. So you see that if you have cyclic group, so G equal to say generated by an element G. Okay. So obviously, for if G is infinite, then if G is infinite, and this implies order of this small g is also infinite. Okay, and so this is not the interesting case. So interesting case is that what about when cardinality of g is finite? Okay, and then in that case you see that g is nothing but exactly 1 g square and g power n minus 1, where order of g equal to n, which is nothing but exactly order of g, small g. Okay. So what I'm saying that if you have cyclic group, this finite group, then the elements of g you can write down easily by this notion. So g square means g into g, obviously. Okay. Similarly, g power n minus 1 is g into g into up to n minus product of n minus 1 means g. Okay. And this is obvious because you can easily prove that there. So these elements g square, gi, gj, whatever, these are all distinct elements. Okay. So this claim, so g power I does not equal to g power j for all 0 I j less than equal to n minus 1. Okay, so in between these are all distinct, and the proof is simple, because if not, then g power I equal to g power j for some I and j, and that will gives you that g power some integer is identity which is less than n, and which contradicts. Okay, so let me give the proof briefly. So if not, then what happened? Then g power j minus I equal to identity, and j minus I is still less than n, right? And this is a contradiction to the fact that, so this is uh, this is the contradiction to the fact that this is a contradiction. As order of g equal to n. Okay, so there cannot be any integer less than n for which g power that integer equal to identity. So these are a simple observation. You can easily find out. There are so many such properties. In fact, um, property number 2, that if say order of g equal to n, and you know that for some integer m this is identity, and this implies n must divide m. Okay, and these proofs are simple again. This is, you need to use something called division algorithm. Okay, just so how to prove this kind of thing? So division algorithm, or Euclidean algorithm also you can say. Okay, due to Euclid. Okay, so due to Euclid, that's why it's called Euclidean algorithm. So that tells you that given any integer m, you can write down as some quotient into n plus remainder, and the remainder is of the form, okay, of this form. Okay, now g power m equal to identity gives you what? This gives you the g power n whole to the power q into g power r equal to identity. Okay, but g power n equal to identity already, because this is our n is ordered, so this will gives you the identity, and you are getting only g power r equal to 1. Okay, and the only options for the solution will be r equal to 0, because if r equal to not 0, then it will be a least positive integer. It will be a positive integer which is less than n, and that contradicts to the fact that order of the equal to n. So this gives equal to r equal to 0, and thus so that r equal to 0 means what? That means n divides n. So these are simple proofs. Okay, you can easily find out these proofs. And so interesting part is that if you know that say g power m equal to identity and g power n equal to identity, and that will allow you to find out g power d equal to identity, where d is the GCD. So we write down these symbols. This is nothing but the greatest common divisor. So GCD of m and n. Okay. And again, the proof is simple. You just need to use the fact that D can be written as integer linear combination of m and n. Okay, n. Okay, and this fact you already. I hope you know how to prove this kind of fact. If you don't know, then maybe we will prove it on the live session. Okay, on demand. So this k1, k2 are element of integer. Note that this K1, K2 may not be always positive. It may be negative also. Okay, sometimes 0 also. So these properties you can easily prove at home, and not only that, in fact, so what else I should say here? So order, yes, yes. So yeah. So and one more property you can ask. So uh, suppose you know that order of g equal to say n, then you can ask what about order of g power say some any power. Okay, the answer is actually n over GCD of NA. Now how do you prove this kind of things? So these proofs are also not very difficult. So you just write down D equal to GCD of NA, and that will tells you that n equal to something d1d and a equal to something d2d, right? With what? This is the greatest common divisor. So what does that mean? That means there cannot be any common factors between d1 d2 other than 1. Okay, so d1 and d2 are co-prime. So d1 d2 are co-prime. Okay, now with this fact, if you want to prove that the order of this equal to this, so let me just start that. Suppose my so I'm writing this symbol h by g power a. Okay, so I need to prove that order of h. What is the order of h? Now you check that if you go with the h power this n by d, which is GCD of n and a, and that you can write down the g power a power n by d, right? But a, if you check that what is a, so a equal to d2d, so you can write down that g power d2 and n, but g power d2n is nothing but g power n into d2, but g power n equal to identity, so this gives you identity. Okay, so what does that mean? That means this n by d, this divides whatever the order that thing divides, right? So let me write down the order is k, for example, and we need to prove that n by d is equal to k. But here I just proved that n by d divides k, right? Now similarly, uh, you can use the fact that, so again, as order of h equal to k, so you know that h power k equal to identity, right? But what is h power k? So h power k is nothing but g power a k, which is equal to identity, right? But order of g equal to say n, and this gives you n divides ak, because order of an element always divides any other one, right? That was proposition properties 1. Now you try to split this thing. So what is n? N equal to your n equal to your d1 d, and a equal to your d2 b, right? So d gets cancelled, and this implies that d1 divides d2 into k, right? But again, you know that d1 and d2 are co-prime, and that implies that um, d1 divides k, right? Clear? But what is d1? You check d1 is nothing but n by d, and so that divides k. So thus nothing. So what is the conclusion? N by d is nothing but, sorry, n by d is nothing but k, which is nothing but order of g power a, right? Clear? So these properties are simple. You can easily prove hundreds of such properties. Okay. Now I am interested to discuss one nice ideas. Okay, so yeah. So now let us little bit play with a group and a subgroups. So you can, obviously, if you have further doubts, you can discuss with me on live sessions. Now let me just okay. So now let me start a new idea. So let me assume that you have a group G and you have a subgroup H. Okay. Now now question is that are there some nice equivalent relation can we define on this or not? So let me just do some checking. So let tilde be a relation on G defined by, so I am defining tilde. Okay. So how I am defining tilde? So I am saying that um, G related to G dash if, say here if means if and only, okay, if G equal to some G dash of H for some H belongs to H. Okay, so this I am defining. I am saying that two elements are related if one can be written as the product of the other element with an element of the subgroup H. Okay. Now you check that. So now this is easy to check that this is a nice relation. So this is first of all reflexive, that is obvious, okay, because for any element G is related to G, uh, for all G belongs to G, as you can write down G equal to G times identity, right? It's obvious. And now you can ask about symmetric properties. So symmetric property, okay. So for symmetric property, what you can do? So you can um, yeah, you can check first if you have a for example, suppose so let you know that G related to G dash. So you want to check that G dash related to G or not. Okay, so this implies you have G equal to some G dash H. But again, you know that H is an element of the subgroup H, so H must have an inverse, right? So you can talk about H inverse. So this implies G dash is nothing but um, G H inverse, okay. And now you see that this H inverse also again an element of H, right? And this implies that G dash is related to H G, okay. So this tilde is symmetric, okay. And similarly for transitive property, you can also find out transitive. The transitive property, how to find out? So suppose you have say G1 related to G2 and G2 related to G3 for some G1, G2, G3. Okay, these are arbitrary. So I'm not saying that these are for one. This has to do for all, say for any, for choose any G1, G2 with this property, and from here you will find out that G1 equal to G2 some H1. From here you will have G2 equal to some G3 into H2, right? And this H1 and H2 are element of H. And these two, if you club these two things, you will have G1 equal to G2 H1, but G2 equal to G3 H3, so it will be nothing but G3 H2 H1, right? By H3 H1 again you can write down as H3, so this is H3, where H3 equal to H2 H1 is again element of H, okay. Now you see that obviously this implies that tilde is transitive, okay. So what does that mean? That means this tilde is an equivalent relation, equivalence relation, right? This is the important outcome. So the moment I have an equivalent relation, so I can talk about the equivalent classes. So now let me see how this equivalent classes look like. So the equivalent class, equivalent class of some elements, say G belongs to G under this tilde. So is so how it look like? The equivalent class is of this form. So this will be nothing but um, all those elements G dash belongs to G, such that what do we mean by equivalent class? So those elements which are related to G, right? So this will be all those G dash such that G dash will be G times H for some H belongs to H, right? This is the meaning of the equivalent class. Okay, but what is this set? This set is nothing but GH. See, this by definition, this is the set GH. GH is what? This is nothing but the product collection of all the elements of the form G times some element of H. Okay, so the equivalent class of an element is of this form GH. Okay, and this has a very nice name. So this GH is called the left Cosets of um, yeah so H um, for G, one of the left Cosets of H in G, right? Now again you remember that equivalence does one more thing. It partition the group G, right? So again we know that equivalence relation um, forms a partition on the set. So therefore we have what we have. So we have that you can write down G is union of these equivalent classes GH. G belongs to G. Clear? And again, because this partition, again you know that either two are same or disjoint, right? So this is partition. So this is not only this, that either this gives you the main one of the nice property, that if G1H equal to G2H, that means if the two equivalent classes are same, that means this implies that G1 must be related to G2. Okay, and that is nothing but telling that G1 equal to G2 times some H. Okay, some H, and again this implies that um, um, G2 inverse G1, which is H and is the element of H, right? So these properties are simple. It is coming from directly that. So what is the conclusion? That G1H equal to G2H if and only if G2 inverse G1 is the element of H, right? Clear? So in particular AH, see if we start with any elements, or say GH equal to H if and only if G belongs to H, right? So this is a particular case of what we proved just, and these properties are nice. So the Cosets are nice properties. You can easily find out many properties other, like if you multiply two Cosets, how it look like. So if you multiply some G1H How do you multiply? So you just give this multiplication rule by g1 g2 of each. Okay, so by this you can give multiplication rules on that thing, right? So 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 this is obvious that you can collect all those cosets, and you want to know how it look like. For example, uh, um, okay, so maybe I will stop here because I want to discuss two more important things that is not possible today. So let me stop here so far, whatever we discuss. So today we have discussed this started with the properties of homomorphisms. Okay, properties of homomorphisms, and yeah. So let me find out. Yeah. So what is this? Yes. So properties of homomorphisms, and then we define something called fiber, and there is a special fiber, it's fiber of identity of G2, which is called the kernel. Okay, and then and and then what? Then we define order of an element. So okay, and then we define the properties of those order of elements. Okay, using division algorithms. Okay, and then for a subgroup we define just uh, an equivalent relation, and we define something called cosets. Okay, so okay, this ends today. So maybe we will define a structure on this collection of cosets and their properties next class. Okay, okay, bye.